Network Plus series, wide area networking. Well, we're getting pretty close to the halfway point of this Network Plus Nugget series, and so far we spent a whole lot of time talking about the local area network. Well, now it's time to expand our horizons, broaden our view of networking as we look at a data communications network that functions beyond the geographic scope of a local area network, beyond the different rooms of a building or the floors of a building. And there's really three major characteristics of wide area networks. WANs connect devices that are separated over wider geographical areas. WANs also use the services of carriers like telephone companies, cable companies, satellite systems, network providers, and service providers. And WANs typically use serial connections, the kinds of serial connections we saw earlier in this Nugget series. And they use connections of different types and different topologies to provide access to bandwidth over those large geographic areas. This nugget on WAN Technologies is going to be broken up into three main areas. First of all, we'll look at some of the common properties of wide area networks. We'll look at some of the older WAN standards, some of which are still in use today, but we're going to cover those first, and then we'll look at the more prevalent and common or ubiquitous wide area network technologies. Sound good? All right, let's do it. Now, a lot of times when people think about a wide area network, they think of the internet, but that's not necessarily the case. Wide area networks have been around for a long time, connecting organizations that span large geographic areas. For example, they could historically use leased lines, or they could use the telephone company. So we know that WAN facilities are provided by a lot of different types of carriers, and we also know that WANs carry a variety of traffic types. We know they carry data, packetized data, but they also carry video and, more prevalently, voice. So as you can see here, we've got our local area networks that we've spent quite a bit of time talking about. But our local area networks usually connect to some type of router that connects across a wide geographic area. Now, our routers can connect to the internet, the global untrusted internet, but a wide variety of carriers, I'll just put a cloud here, a wide variety of carriers can connect our wide area network together. As I mentioned, these could be telcos, they could be public carriers, they could be service providers, they could be cable companies, a wide variety of solutions. And WANs can do more than just connect buildings together. They can connect the main office to things like business partners, remote offices, and these can be global extensions of the headquarters. They can be extensions of thousands of remote workers or teleworkers. They can be regional offices or branch offices, home offices, and other types of temporary mobile workers. So why do we need wide area networks? Well, as we learned, LAN technologies are going to be fast, they're going to be cost efficient, and they transmit data in our organizations over a relatively small geographic area. Several offices in a complex, several buildings on a campus, several floors of a building. But there are other business needs that extend beyond the local area network. As I mentioned, you might have regional or branch offices of let's say, a insurance company that has lots of satellite offices, or independent insurance agencies. Organizations may also want to share information with certain strategic partners, or vendors, or large customers that are over large distances. For example, a software manufacturer might communicate their product information and inventory information or promotional information to distributors that sell their products. And of course, there's employees who travel on company business all over the United States, for example, or all over your country, all over the world. And it's also becoming much more common for home computers to be converted into the small office, home office, or teleworker solution. And one other thing, the local area network is typically a single geographic area or single business, but it's also typically completely owned by the organization. However, a wide area network may be a shared ownership. So you're subscribing, this cloud here may be owned by some other carrier or service provider. So there's a shared ownership, and it involves things like service level agreements between the customer and the provider. So for example, you might have your central headquarters here, which has, 1,000 plus users. And this connects to other buildings on the campus or other floors of the high-rise building, maybe using some fast LAN technology like FIDI or a fiber ring. So we're using a ring topology, and we're using fiber for our high-speed connectivity to buildings or floors of a building that are typically geographically closer together. But then we might have connections over large geographic areas using, let's say, DSL or cable connections to a remote office, branch office. We've got other WAN or long-distance Ethernet connections to other buildings, extensions of our headquarters. These could be branch offices, regional offices, satellite offices, vendors, partners, or large customers. Of course, don't forget out here, we've also got the small office, home office, and the emerging teleworker solution, and the remote employee getting remote access from a wide variety of locations over the wide area network. Let's say using their laptop to access from an airport, or a hotel, or a conference room, or a kiosk, or a coffee shop. Now, there are 5 main WAN properties that CompTIA wants you to know for the Network Plus exam. And these are things that can help differentiate different WAN technologies from one another. These are general categories. Things like circuit-switched WANs and packet-switched WANs, the different speeds that wide area networks support, the transmission media, which can vary greatly, and of course the distances that are supported. Now, one thing that makes a network circuit switched is the fact that, in contrast to a packet switch network that we'll look at here in a second, circuit switch networks have the data path established exclusively for use between 2 communicating devices. A good example of this is when you make a telephone call using a standard landline. Okay? You've got a dedicated path or circuit between you, the caller, and the person that you're calling. Okay? And that circuit is established for the entire duration of the call. No other users can share this circuit. Also, a circuit-switched connection link is dynamically established, and it's a dedicated virtual connection for voice, as I mentioned with telephony, or data between the sender and receiver. And so, with a circuit switch network, before the communication can even begin, you have to establish the connection through the network of the service provider. So, for example, with your telephone again, as you pick it up and you hear the dial tone and you dial the number, there is a signaling process that takes place and a circuit is created. Now, in a packet switch network, the data is going to be actually transmitted in labeled envelopes, okay? And a packet switch network will send these in these labeled, they can be cells, which is used with ATM, we'll talk about. They can be sent in frames. They can be sent in packets. So different types of devices obviously participate. A different type of device or intermediate device, call it a router or gateway, does circuit switching than the device that would do packet switching. So in a packet switch network, you have a physical dedicated circuit. A physical dedicated circuit between the sender and the receiver isn't necessary. We use logical virtual dedicated circuits instead. So the same data path could be shared by multiple users in the network. This is in opposition to a circuit switch network. So with packet switching, the data transmissions are actually broken down into individual packets, and you've got addressing information inside of each packet, and this is used to route the packets to its destination. In the packet switch network, a physical dedicated circuit between the sender and receiver isn't used. It's not necessary. We use logical virtual dedicated circuits. A widely used circuit switch network over the global landscape that is considerably a legacy or an older technology is X25. A packet switch network could be something like ATM that uses cells, or frame relay that uses, well, frames. It relays frames. Now there is one other type of wide area network that's not on the required list for the Network Plus exam, but I want to go ahead and mention it here anyway. And we don't see these much anymore because they're just so darned expensive, but this is what we used to use early on in the early days of the internet, okay? These are what are called dedicated links, or leased lines. Okay, leased lines. These are dedicated permanent connections, point-to-point lines that are limited only by the underlying physical facilities and how much money the users have to pay for the dedicated lines. So a point-to-point link provides a pre-established dedicated WAN communication path from the customer premises through some type of provider network to a remote destination. Now you'll see these used in highly proprietary environments, maybe the military, certain government implementations. These are private, dedicated leased line networks. They're expensive, but they're very secure. So these point-to-point lines are usually leased from a carrier, or a provider, or a telco. That's why we get the name leased lines for these dedicated links. So with dedicated links, we would use what are called leased lines. The most common and ubiquitous circuit switched network is the PSTN. So circuit switched is going to use the PSTN, the public switched telephone network. This is the planet's public circuit switched telephone network. It's kind of the, if you think about the internet as being the world's public IP-based packet switch network that's global, that's what the PSTN is. Now, it used to be made up of fixed-line analog telephone systems, but now the PSTN is almost entirely digital. Also includes mobile phones as well. The most common packet switch networks are going to be frame relay, your cable system, and DSL. Okay, these are technically packet switch networks. I mentioned ATM as kind of being in this packet switch category, but technically ATM, or asynchronous transfer mode, is technically cell switched because it doesn't use packets. Okay, it uses cells. This is important terminology to understand for your exam. Now, one thing that sets WANs apart is their speed, and local area networks we know are, fast Ethernet, 100 megabit per second, all the way up to, as we know, Ethernet's up to the 10 gig now. But wide area networks can be as slow as a 56 kilobit per second link using a dial-up modem. These are going to be generally in the range of 256 kilobit per second, maybe up to 512. You've got T1s and we're going to talk about T1 and T3, but T1s, this is a 1, not a 2. T1s and T3s, these are, 1.5 megabit per second and higher. And again, this is a lot slower speed than 100 megabit per second fast Ethernet, or 10 gigabit or even gigabit Ethernet, which is 1,000 megabit per second. So typically, historically, wide area networks, because of the geography and because of the cost, have been slower. Now we're seeing WAN networks get faster, okay? But this is one of the things that sets it apart. For example, if you're going to a provider, the more speed you need, the more money it's going to cost you. And that's not so much the case in a local area network. I can just basically put in fiber or gigabit or 10 gigabit Ethernet, and I can get that speed with just changing over the cabling and maybe some modifications to network interfaces. But for high speeds from a public network, the PSTN, or high speeds from a provider, the faster the bandwidth, the more the bandwidth, the more money it's going to cost you. So speed sets these things apart. The transmission media also. We know that we've got serial cables, and I showed you a wide variety of different serial cables in a previous nugget. But we've also got a lot of fiber optic options as well. For example, single mode fiber is starting to find its way into wide area network connectivity. So transmission media is typically going to be different than you'd see in a local area network, and different types of circuit switched, packet switched, and cell switched networks use different types of transmission media. And of course, distance. We already know that, for example, multi-mode fiber isn't going to go as far as single-mode fiber. So different WAN technologies will support different distances at different speeds. So these are all general terminologies that we have to know before we start to look at some of the granular WAN technologies, in which we're going to do that right now. Let's start out by looking at some of the legacy, or some of the, we'll call it soon to be retired WAN technologies. You might be wondering why I use some of these pictures I use in the upper left-hand corner. Sometimes I just grab little pictures that I like. They have no significance whatsoever to the topic I'm talking about, and I apologize for that, but I'm just kind of using just to get some eye-catching graphics and, obviously change up some of the monotony of using just whiteboard so much. So I apologize for some of these wacky pictures I'm showing you, but I think it helps. Now, we're going to look now at some of the soon-to-be retired or older WAN technologies. And again, some of these are still in use. Some of these are widely still in use, especially when you move out of the metropolitan areas, maybe other countries. But we need to know these for our exam and for the real world. Let's look at some what we call older WAN technology, and this isn't necessarily out of date. It's still used. It's kind of legacy. It's been around a while, and we're going to look at the first two here, which is POTS and PSTN, which are really kind of synonymous. These are the most common types of circuit-switched WAN communications, okay? PSTN is the public switch telephone network. It's also referred to the POTS, the plain old telephone service. And what you can see here, what we've got over here in the diagram, this is what we call a PBX. This is what telephone systems use. Here's our local exchange over here, or our telco. What we have with POTS and PSTN is when you have intermittent and low volume needs for data transfers, and you're using asynchronous modems and using analog dial telephone lines for low capacity, on demand, dedicated switch connections, you can fall back on the old POTS. This is your traditional telephony using a copper cable, which is called a local loop, that connects the telephone handset at the subscriber's premises to the telephone network. Now, the local loop here is not suitable for transporting, binary computer data. But what you can see we have here is a modem. And the modem, which means modulate, demodulate, it actually modulates the binary data from the PC into the analog signal at the source end here, and then it demodulates the analog signal to binary data at the receiver. Typically, you're going to get about 33 kilobits per second bandwidth. However, you can get up to 56 kilobit per second bandwidth. And for a small business, a small office, home office, maybe a rural site that doesn't have any options because they're not close to a metropolitan network, metropolitan area, then the PSTN could be adequate. Maybe to upload sales figures, routine reports, basic email, and maybe some thin web services. So the advantages to POTS and the PSTN is that it's simple, it's readily available everywhere, it's low cost. However, the disadvantages are you only get low data rates, maxing out at 56K per second. There are some ways that you can combine lines, combine channels. Relatively speaking, it takes quite a long time to set up the connection, longer than other WAN connection types. Now, for years, a great alternative to the modem through the plain old telephone service, POTS and PSTN, was the ISDN basic rate interface. The Integrated Services Digital Network provides the home office, small business with better speeds, okay, 64 kilobit per second up to 128 kilobit per second. And you can see here we've got all of our LAN devices, and here's our kind of our ISDN equipment specifications. Now on the telephone line, ISDN BRI is divided into 3 digital channels. So I'm just going to put 3 channels here. You're going to have a D channel, which is basically the command and control channel that sets up the call and cancels the call. And then you have 2 B channels. And these can transmit data at a rate of 56 to 64K per second. Then also you can combine these B channels, and that's how we get that 128K connectivity. Now, primary rate interface, PRI, actually uses 23 of the B channels and 1 D channel. And these B channels can carry voice, they can carry data, and the maximum transfer rate for ISDN PRI is 1.544 megabits per second. And that just so happens to be a T1 connection. And as a matter of fact, a lot of organizations will get what's called fractional T1. So they're going to pay for or subscribe to a certain number of these B channels. So for example, if they want to get 4 B channels, they can get 256K of bandwidth. Now ISDN is not necessarily universally available. You have to have a certain kind of equipment installed. The provider has to support it. And by the way, most phone companies are moving away from ISDN towards things that we're going to look at in the next section, which would be things like DSL. But ISDN does use what's called circuit switching. You might have separate phone numbers for each one of your lines. As a matter of fact, sometimes a business will use the D channel just for, let's say, their alarm system or something. And then you'll have what's called an SPID or a SPID, and that'll be given to you by your service provider. It's the Service Profile Identifier. Those are used in the US and Canada. Now, ISDN hardware typically nowadays is going to be integrated into the router. So typically your newer routers will have an ISDN module on it. So it includes all these interfaces. It includes the ST interface and the U interface. In older implementations, these would be separate devices. So the components of ISDN would be kind of partitioned into separate components. Some of them would be on the customer side, some might be on the service provider side, so the demarcation point could differ. So this U interface here traditionally carries ISDN signals over a single pair of wires for long distances, like between your office and the provider's central office. However, most of the ISDN adapters that go into your routers today have the U interface built into them. The SD interface stands for Subscriber Termination Interface, and this uses 2 pairs of wires for shorter distances, for example from the wall jack to your ISDN equipment. And again, today most routers have all of these components built into them. Next we have frame relay, and frame relay is a layer 2 or data link layer WAN technology. It's a packet switched technology, and it has been very popular throughout the 90s and the early years of this millennium. It replaced older technologies like X25 that we don't even mention here, X25 and leased lines. It was much more cost effective, and it provided higher bandwidth and lower latency packet switching. Service providers, like the one you see here, could provide what are called permanent virtual circuits, PVCs, or switched virtual circuits, using some shared medium width bandwidth connectivity carrying both data and voice traffic. The data rates were typically up to about 4 megabits per second. Not bad. A huge jump up from the POTS and the ISDN solutions. Also, frame relay is a lot simpler to implement than other protocols that work, let's say, at network layer 3. Most frame relay connections are permanent virtual circuits as opposed to switched virtual circuits. With the frame relay virtual circuits, what you have at the customer premises is the DTE device, the data terminating equipment, and what you would have at the provider is what's called the DCE. And the layer 2 addressing that we use is not a MAC address. We use a data link connection identifier, a DLCI, a DLCI, and these DLCIs are locally significant. So I could have DLCI 157 here, I could have DLCI 723 here, DLCI 733 here, and so on. In other words, these endpoints do not know the other site's DLCI number. Frame relay is still widely used, it's ubiquitous, but like its cousin ATM, it's on the way out in lieu of newer, improved services. Let's talk about ATM or asynchronous transfer mode while we're here. ATM is actually not a packet switching or a circuit switching connection. It's called a cell switching technology. It's capable of transferring data and voice and video over public networks and private networks. ATM is used still widely used in enterprise local area network backbones as well as wide area network links. One of the advantages of ATM is it can get data rates well beyond 155 megabit per second. From a topological standpoint, as you can see our ATM switch here, it does look a lot like frame relay. But again, it's built on a cell-based architecture. These ATM cells are always fixed lengths of 53 bytes. And small fixed length cells are actually excellent for carrying voice and video traffic because this type of traffic has no tolerance for things like delay. So with the 53-byte ATM cell, video and voice traffic doesn't have to wait for a larger data packet to be transmitted, like in frame relay. There is a downside, though. The 53-byte ATM cell is less efficient than the larger frames and packets of frame relay and even X25. Also, ATM cells have at least 5 bytes of overhead for every 48-byte payload. Like frame relay, ATM is also implemented using virtual circuits that can be permanent virtual circuits or switched virtual circuits. But instead of using a DLCI for an identifier at layer 2, the ATM cell header contains a field called the VPI VCI. And that's the virtual path identifier, virtual channel identifier. Now at the physical layer, ATM can run on top of a wide variety of physical media, for example fiber optics, and we'll talk about SONET here on the next screen. Again, although ATM is still widely deployed, it's on its way out. T1 is also referred to as DS1, which is Digital Signal 1. This is a T carrier scheme devised by Bell Labs. It's widely used in North America and Japan to transmit voice and data between devices. Now, outside of North America, Japan, and South Korea, they use what's called E1. The DS1 or T1 circuit is made up of 24 8-bit channels, each channel being a 64 kilobit carrier circuit. So it can ultimately carry 1.544 megabits per second. Now at T3E3, this is known as Digital Signal 3. This is a Digital Signal Level 3 T carrier, also referred to as a T3 line. Outside of the US, it's an E3, and this has a data rate up to 44.736 megabits per second. A T3 can carry 28 DS1 signals in the payload, or 28 T1s, and this level of transport or circuit is typically used between telephony carriers in both wired and wireless implementations. DSL is a family of technologies for digital data transmission. DSL stands for Digital Subscriber Line. There should be an S, subscriber line. And there are a bunch of different flavors of DSL. You've got ADSL, SDSL, VDSL, among others. This is a widely adopted solution, ADSL being the more popular, and you can get this from your phone company like AT&T, for example. ADSL stands for asymmetric digital subscriber line, which basically means it's asymmetric transmission. You're going to have a faster download and a slower upload. Whereas symmetric digital subscriber line is going to have the same bandwidth going up and going down. DSL typically has multiple bands, so it can carry voice and data. So a DSL modem and a normal telephone can be used simultaneously on the line without interference from each other, as long as you have the DSL filter on the phone. VDSL, which is the third option that CompTIA wants you to know about, stands for Very High Speed Digital Subscriber Line. And this is a DSL technology that provides faster data transmission over a single flat untwisted wire or twisted pair of copper wires. So you can get high bandwidth things like high def television and voice over IP using the plain old telephone service. It uses some special types of modulation techniques, and you can get data rates exceeding 100 megabits per second. Now, another emerging solution for the small office, home office, remote office, branch office like DSL and the different flavors is cable, using the cable modem that provides bidirectional data communication. It uses RF channels, radio frequency, on a cable television infrastructure, or CATV. Now, typically cable modems are used to deliver broadband internet access like cable internet, but throughout North America, cable is also being used to provide other services as well. For example, low-cost internet services to the regional office, remote office, and branch office solution. Cable uses a specification for handling its communication called DOCSIS. Probably should know that for the exam. This stands for Data over Cable Service Interface Specification. This is an international standard that supports the communication and operation of data over a cable system. You're also seeing cable modems combining voice over IP solutions as well. Satellite is also a solution that's being used for wide area networking. As a matter of fact, Motorola has a proprietary service called Canopy, which is used for wide area network. It's a line of sight technology, so you have to see the tower. And of course, satellite can also be used for the satellites that with a dish that are going to point to the satellite that's moving in orbit around the planet Earth. Satellite is also asymmetric, like DSL, in the sense that you're going to have much faster downloads and slower uploads. So it's an asymmetric technology offering various bandwidths as well. Now, OCX and SONET kind of move hand in hand. A SONET line is a fiber optic line, and OCX stands for different flavors of optical carrier using optical fiber. So you've got OC1, OC3, OC12, OC24. Obviously, the larger the number, the higher the transmission speed. So OC1 is going to give you speeds of about 51.8 megabit per second. OC3 is faster, 155 megabit per second. OC12, 622 megabit per second. OC24, 1244 megabit per second. OC48, 2488 megabit per second. So these just go up higher and higher and higher. And this is part of the SONET fiber optic network, which are really used for high bandwidth wide area network communication transport. Now, wireless is also being used for wide area networking, and as I look back to my slide as I was reviewing this, I realized that I mentioned Motorola Canopy up here under the satellite. Actually, Motorola Canopy is a type of wireless technology, a proprietary wireless technology. Now I'm going to talk about wireless in its own dedicated nugget coming up after this one. So the last thing we're going to talk about here is really one of the emerging technologies for a wide area network. This is moving from the service provider now into the enterprise, and that is what we call multi-protocol label switching. And this is basically a highly scalable, and it's independent of the protocol mechanism for carrying data. And the data packets are basically just assigned labels. And actually, in the data packet header, the label is kind of shimmed in there, or kind of inserted in there at data link layer 2, and those labels can be used for packet forwarding decisions. And since the packet forwarding decisions are made solely on the contents of the label, there's no need to actually look inside of the packet itself. So it can go on, it can create end-to-end circuits over any type of transport mechanism using any protocol. So the main thing about MPLS is that we no longer have to rely upon certain types of data link layer technologies like ATM or frame relay or Ethernet or SONET. And this is a vastly emerging technology that's becoming much more popular. MPLS belongs to the family of packet switch networks. So it is a packet switch technology. Just to give you an example, AT&T, as of I think a couple of years ago, was the largest frame relay provider in the U.S. And as most of these frame relay contracts expire, most of the customers are typically going to migrate from frame relay to MPLS over IP or frame relay over Ethernet. That's going to be the emerging solution. That's why I put it in the category here under emerging WAN technologies. So for a lot of companies and customers, it'll reduce the cost and vastly improve manageability and performance of their wide area networks. Okay, in this nugget on WAN technologies, we covered 3 key areas. First of all, talked about some common WAN properties, looked at some of the older, still in use, but quickly becoming legacy WAN standards, and then looked at prevalent or common or emerging WAN technologies. I hope this CBT Nugget's been informative for you. I want to thank you for viewing. See you next time.